We're back. We are still in section 30.3, talking about the possibility of life out there in the universe. We talked about life in our solar system, some good places to look, Mars and some of the moons. Today we are going to go beyond and look at the possibility of life on planets around other stars, exoplanets. So exoplanets is sort of short for extrasolar planets. Extrasolar means not our sun, in other words. So these are around other stars. And this is a really super exciting field in astronomy because it's pretty new. We've only known about these stars for a few years relatively. It was in the 90s when we first found a star that had planets around it and confirmed that. But since then we have found thousands of these things. And we find more every day, and I'll tell you about some of the latest discoveries and share some videos with you on some of the most exciting of these exoplanets that we found. But what I really want to focus on today is how do we dig through all these planets, thousands of planets, and find good candidates for life. There's a couple of space telescopes, Kepler, which is retired now, and a new one called TESS. And they have found all these planets around suns, but they are not all good candidates. How can we sift through all that and find planets that are maybe like Earth, that meet the criteria we talked about last time, that have things like liquid water and heat and atmospheres and even some of those molecules, carbon-based molecules? Well, we're going to really focus on sort of that idea of liquid water and temperature. And there are several things that we can actually learn about these planets without going there, without taking pictures of the planets, just from our space telescopes. And one of them is we can figure out what the orbit looks like of these planets. Because we know that if you have a stable orbit that's almost a circle, that should be an R, stable circular orbits. I'm going to introduce a term here because I have an activity lecture tutorial and I just want to make sure you know all the terms on it. A small eccentricity. So when you have something that's not a perfect circle, it's an ellipse or an oval type shape, but if it's just almost a circle, just slightly elliptical, then we say it has a small eccentricity. If it gets too elliptical to oblong, then you have problems. So we want a stable circular orbit. And this is what our Earth has. Earth has a very small eccentricity because we don't want to be going way out away from our star and getting really cold and then coming back in close and getting hot. Because if you have really elliptical orbits with big eccentricities, very oblong type of things, then you get huge swings in temperature. So when we're looking for life, we want a stable circular orbit because elliptical orbits are bad. Elliptical orbits cause big temperature changes. So close to circle, good. Not a circle, bad. And this is something that we can actually observe with the information that we have, okay? So we want something that's like Earth with a small eccentricity. We don't want to be going through an ice age every year, is another way to put it. Okay. The second one is we want the right temperature for liquid water. So even that stable circular orbit, that's about temperature too. You don't want big temperature changes over the year, but we also want the temperature to be just right. We want our planet to be in the habitable zone. So the habitable, or it's sometimes called the Goldilocks zone, because it's not too hot and it's not too cold. It is just right for what? For liquid water. So the habitable or Goldilocks zone really describes how far away the planet orbits. So it's the distance of the planet from its star. Okay. And when we do our activity, we're going to call this the semi-major axis. That's just a mathematical term for how you find a distance from the center to the edge of an ellipse or an oval, because it's not the same everywhere. Okay, so the distance from the star or the semi-major axis, where temperature is just right for liquid water. On the planet, we on Earth are in the habitable zone of our sun. So our sun has a habitable zone. It's this blue thing here. And so the sun is over here. Sun. All right, there's Mercury, Venus. Earth is in that habitable zone. It's just the right distance so the temperature is right for liquid water. Mars may have been in a habitable zone before because our sun may have been different, but right now we're the only one there. Remember we talked about those moons around Jupiter and Saturn? They are not in a habitable zone, but they might have a good temperature just based on internal heating. And that's sort of a different story. But we're just talking distance. This is the semi-major axis right here. Distance from that sun. Okay? Now, habitable zone. I'm going to take a little break here and show you something interesting that one of your classmates just sent me. We are always looking for planets that are in habitable zone and that are the same size as Earth. We'll talk about that in just a minute. And recently, just in the past couple weeks, NASA has released some data. Kepler's that old space telescope of a planet that looks a lot like Earth. This is the kind of thing we're looking for here. It says in particular that this one is in the habitable zone. Okay, so it's the right distance. It's only a little bit bigger than Earth, and it gets about 75% of the amount of light that Earth receives, so its temperature may be similar to ours. But it orbits a small red star. Think those K&M stars at the bottom of the HR diagram. So that's going to change things. We'll talk about the type of star too, so watch out for that. But there's a lot we don't know. We don't really know about its atmosphere, what's going on there. We think it's a rocky planet. It's about the same size. So this is a really interesting candidate. There are some other interesting candidates too. The TRAPPIST system, I have a video on that I'll share with you guys. But we are finding these planets, and as we look closer at them, we are finding ones that look a lot like Earth. If you want to help, you can go, I'm going to share this link with you to this video. This video is going to explain the work of this new planet hunting telescope called TESS. And you can actually go, this Zooniverse is a site where you can participate in research, not just astronomy, all kinds of science, history, sociology, all kinds of cool research that you can participate in. One of the things that you can do is look for planets. And the video will explain how this works, but you're going to look for transits. Transits are when you got the sun shining here. This is the star. It's shining, 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 shining. And then all of a sudden, look at this. You see this right here? There's this big dip. That tells us that something dimmed the star. The brightness of the star went down right here, and that is potentially a planet passing in front of that star. So that's how we find these planets. And then from that information, just from all these dots and wiggles, we can figure out how big it is. We can figure out how far away from the sun it is. And we can also find some information about that star itself. Okay, so back to our notes here. We have so far two criteria: a stable circular orbit, and it's in the habitable or Goldilocks zone. The third criteria here is that the planet is the right size. This is pretty important. Just think about our own solar system. The planet has to have the right mass and the right radius, okay, or diameter, its size. Because if we're going to have life as we know it, we need a rocky planet with a small breathable atmosphere. Okay? We do not need a planet that is all atmosphere, a planet like Jupiter or Saturn with no surface. Right? If we have a planet that is too big, too large of a planet, then it is almost always a gas giant. That's true in our solar system, and we believe that's true in other solar systems as well. On the flip side, if we have a planet that is too small, then we know from physics and from looking at things like Mercury and the moon that you're not going to get an atmosphere, that you don't have actually enough gravity to hold on to the gas. We want some oxygen and other good stuff in our atmosphere, but if your planet is too small, it won't hold on to it. No atmosphere. So we want something that is just right. And here's a little graph showing the sizes of some of the planets and some of the planets that we've actually found around other stars, right? These are Earth size. These are the big gas giant size. But look here in the middle. We have found a lot of planets that are in between Earth and Neptune. Neptune is our smallest gas giant. What are these guys? That is a big mystery. Are they gassy or are they rocky? So sometimes these are called super Earths or mini Neptunes. I'm just going to write down the term super Earth. I like that one better. Sometimes they split them into two categories, but in general, these super Earths are things that we don't find in our solar system, but seem to be really common elsewhere. So that's a bit of a mystery. They are in between rocky and gas. So they are bigger than Earth, smaller than Neptune, bigger than Earth. Scroll down here. So bigger than Earth, smaller than Neptune. And we don't know, are they gas or rocky? That is a mystery. So we don't know if these are good places for life on Earth or not. So sometimes size is not the best criteria. Okay. Next, our fourth criteria, stable circular orbits, habitable zone, right size planet. The last one is the right type of star. Okay, so the right type of star. So now we remember our types of stars, right? We have O be a fine guy, kiss me, right? O stars, the big hot blue ones. G is our sun, and at the far end, the cooler red ones. So the right type of star is one that lives for a long time. We don't want a star that explodes as a supernova after only a billion years. Not really enough time to do much. But we also want a nice, big, good-sized habitable zone. And remember, a habitable zone depends on distance from the star, but it also depends on the temperature of the star. Because if you have a really hot star, then you're going to have a big, hot habitable zone, right? Or not hot habitable zone, but a bigger habitable zone. So when we have those high mass stars, those O and B type blue stars, high mass stars, they are great because you get a big habitable zone because you have lots of heat, lots of place for that planet to be where you can have liquid water. So you have a bigger habitable zone. But if you remember, these guys do not live very long. So that is not good for life. Even if life were to develop, then the star goes supernova, done. Sorry. But probably not even enough time for life to develop based on what we understand on Earth. So what about low mass stars? Well, our sun is a low mass star, but it turns out there's a lot of stars out there that are even lower mass and even cooler than our sun, those red dwarf stars. So these low mass cooler stars, they have smaller habitable zones. They're also closer to the star. As you can imagine, it's a cooler star. The habitable zone sort of creeps in a little bit. So smaller, closer, habitable zone. But they live for a long, long time. So that's a really great thing. And research suggests that there could be 100 billion of these really cool stars just in our Milky Way with planets. This graphic is just sort of showing you these cool red, orange dwarf stars, how close the habitable zone is to them. And then it moves further out as we get something like the sun. But we see a lot of these guys with planets. So very intriguing, including that new one that I just showed you in the article. So now I'm going to show you a clicker. I'm going to zoom past a couple of slides. I'm going to do a separate video for the lecture tutorial this week. This will be your clicker. And then if you need the lecture tutorial points, you can watch the other video on that. All right, check out those videos on the planets too. They're awesome.